Okay, does anybody remember the 3 kind that we talked about? Trying to get the chat up. Okay, what do we got in the chat? Dipole, yep. London dispersion and hydrogen bonding. Those are the 3 kinds we talked about. And as a reminder, hydrogen bonding is the strongest. London dispersion, or van der Waals, as they're also known, as the weakest. And then what we did, to remind you, is we examined different molecules. And we said, how do we know what kind of intermolecular interaction will be the strongest for them? And why does it matter which one's the strongest? Because that's what affects how much energy or heat it will take to boil or melt substances. And so that's how their physical properties are affected, depending on what is the strongest type of force that's holding identical molecules of a particular substance together. Okay, so we did A, B, and C together, and then I had you do D, E, and F. And you would draw out the Lewis structure. You would ask yourself these kinds of questions. Does it have the requirements for hydrogen bonding? What are the 2 requirements for hydrogen bonding? Anybody remember? To hydrogen bond, you got to have 2 things. You've got to have a
lone pair.
A lone pair. Yep, seeing in the chat. A lone pair on an oxygen, nitrogen, and fluorine. That's 1. Do we call that the acceptor or the donor? Y'all remember?
Acceptor.
That's the acceptor. So you've got to have an acceptor, a lone pair on an oxygen, nitrogen, fluorine. You've got to have a donor as well. And I think Kathleen put it, you've got to have a positively polarized hydrogen. That is a donor. Okay, so if you have a donor and an acceptor, you can hydrogen bond with an identical molecule that looks just like the one you're drawing. Okay, if you only have one or the other, say you have a donor but you don't have an acceptor, say you have a positively polarized hydrogen but you don't have a lone pair on an oxygen, nitrogen, fluorine, you can still hydrogen bond, just not with yourself. You can hydrogen bond with, say, a water molecule, another molecule that has the piece you're missing. So if you have an acceptor, you could hydrogen bond with a molecule that has a donor. If you have a donor, you can hydrogen bond with a molecule that has an acceptor. Does that make sense? Okay. All right, you don't have to have both. You just have to have one or the other, but to hydrogen bond with yourself, 2 identical molecules, you have to have both. All right, so that's kind of the question this is getting at right here. So we're going to take some more time. We probably are not going to do all of these. In fact, I just want to do the second one and the last one. So we're going to look at CH3NH2 and then CH3O, CH3. Which of these species can form a hydrogen bond in its pure form, meaning with another molecule identical to the one we're going to draw? And then which one can only hydrogen bond with a water molecule? So first off, we'll spend 1 second on this C2H6. If you have a molecule that's just carbon and hydrogen, what do you immediately know about it? Can it hydrogen bond? The correct answer here is, yeah, no. Carbon bonds and carbon hydrogen bonds, none of it's polar. None of those hydrogens are positively polarized. You have no lone pairs anywhere in the structure. So this one, without even drawing it out, just simply because it's only a carbon and a hydrogen molecule, this one cannot hydrogen bond, okay? Can't hydrogen bond with itself, can't hydrogen bond with water or anything. It's not even a polar molecule. So the strongest force there holding molecules like this together are what? Strongest intermolecular force for carbohydrates. Yes, thank you, Jenna. Our London dispersion. All right, so let's actually zoom in and focus on this second one real quick. Take a second, give it your best shot, draw out the Lewis structure here. This is a condensed structure, so it kind of tells you how the atoms are attached. You got a CH3 group, and then on the other side, you got an NH2 group, and those are connected. So if you're trying to draw that out, here's your CH3 group. And then we got an NH2 group. And then that nitrogen should have lone pairs. Okay, so there's our molecule. So now we need to ask the questions. Is this polar? Can it hydrogen bond? So we need to, if it can hydrogen bond, we need to be able to identify donors and acceptors, or at least one or the other. Can anybody identify one of those? Do we have a donor? So like if we do, which hydrogens are the donors?
The
Except
one connected to the nitrogen?
the hydrogens connected to the nitrogens. Yes, Aaliyah. These over here are both positively polarized. Why are these hydrogens not? The carbon-hydrogen bond is not polar. And how do we know this? If this is all back on electronegativity. Remember this chart? Don't forget how to use this. You have to be able to identify the electronegativities, find the difference, subtract the two values, and then the table that you will also have on, you guys remember this table from chapter 4? You'll have this table on the exam. So that's how you know. I was doing a lot of this, I realized, just kind of innately in lecture without showing you this table. But anything that's between 0.5, a difference, electronegativity difference, and 1.9, that's a polar. So polar bond. I think we're right here. So carbon hydrogen bonds are not polar. So none of these hydrogens over here, these are not going to be donors. All right, but these over here will be donors. And then look, we have a lone pair on a nitrogen, so that is an acceptor. So the question is, can this molecule hydrogen bond with itself? Does it have both a donor and an acceptor within the molecule? Yes, it does. Okay, these right here are donors. So this can H bond with itself. You want to see how it does that? Let's actually draw a picture of how it does that. So if we have the acceptor here, I'm going to shrink this down. If we have the acceptor, I'm going to draw another molecule in blue. We would simply take one of the donors and orient it towards an acceptor. Okay, so I'm going to draw another molecule. Here's the NH2. It's not an NH2. Here's the NH2 group of a different molecule. And then I don't really have a lot of room, but you could draw the CH3 group. Okay, and here's where the hydrogen bond comes in, right between these two. Okay, this is our positively polarized hydrogen, and this is our semi-negative because that's where the electron charge is. That's how you would draw these two molecules interacting together, identical molecules in a hydrogen bond. Okay, you would orient the donor of one close to the acceptor of another. Make sense? Okay. If you ever have questions on how to draw that, like if I ask you to do that on an exam, you have two really good examples with water and nitrogen up here. Okay, and that shows you orient the donor of one close to or in proximity to the acceptor of another molecule. Okay, all right. Now I want to look at this last one over here. CH3, any questions on the one we just did? Okay. CH3O, CH3, draw a molecule of that. What does that look like? This is another condensed structure, so it should tell you, if you know, remember how to read those, how the atoms are connected. So you should have something like this. That oxygen is not in parentheses, so it is part of the main chain this time. Okay, does that look like what you drew? Something similar? Okay, so now, can it hydrogen bond? Do we have a donor? Do we have an acceptor? Do we have both? Do we have one or the other? Allison says it cannot hydrogen bond. Is that, you think, no to both questions, Allison? So maybe it can't in its pure form, and it also can't with water, or does anybody think it could hydrogen bond with water? Remember, if you have one piece or the other, if you have a donor, but you don't have an acceptor, you can still hydrogen bond. But if you, vice versa, if you have an acceptor, but you don't have a donor, Tucker says oxygen, I think Tucker, you mean oxygen can be the acceptor. Oxygen could provide, oh, sorry, yeah, oxygen could be the acceptor here. Mary says it can with water, and I agree. So none of these hydrogens bonded to the carbons, okay, none of these. None of those are positively polarized. So we don't have a donor on this molecule. because remember, it's the positively polarized hydrogens that are donors. We don't have one. But we do have 2 acceptors. Each lone pair is a unique acceptor. Okay, oxygen will always have 2 acceptors. Nitrogens will always have 1 acceptor, and fluorines will always have 3 acceptors. So we do have acceptors here. So it cannot, if we're answering this question, the answer is no. It cannot hydrogen bond in pure form. But if we're answering this one, can it hydrogen bond with a water molecule? Yes, it can. Let's actually draw a picture of how it can do that. I'm going to erase right here so we can put a little water molecule in here. And you could do it on either side. I'm just going to show you from the bottom side. Okay, so we have the acceptor. We need to supply the donor. Abby, for an atom to be an acceptor, does it have to be in a polar bond? No, because the acceptor portion here has nothing to do with the bond. It's the lone pair itself. Yeah, so the bond actually doesn't matter. You're just looking for lone pairs. Okay, that's a great question. All right, so we're going to supply the donor, which is I'm on eraser, which is the hydrogen from a water molecule. So I'm going to draw a water molecule. It's kind of crooked, but I'm just trying to orient a donor. So this is a donor, and we can show that by drawing in the partial positive from the water molecule, and the acceptor on our molecule. I'm going to draw a little red dotted line indicating this is the hydrogen bond between the acceptor, abbreviate A for acceptor, and labeling the donor. Okay. So if I ask you to show molecules hydrogen bonding together, and this is exactly what you're going to be doing on the dry lab next week. I don't want you to worry about it right now, but I want you to remember we practiced this in lecture. Okay, you're going to show me how various molecules can hydrogen bond with water. So you're going to use that tool on Mastering Chemistry that everyone loves, and you're going to draw your structure in. You're going to, and I'll do a practice video, and I'll show you a little quick video, and you're going to draw in a water molecule next to a donor and acceptor and show me how it can hydrogen bond with donors and acceptors. Okay. Any questions on that? All right. And remember, hydrogen bonding, because it's the strongest, that if a molecule can do that, that means it's going to have really high melting points and really high boiling points. Okay. So this table is really just a review of the characteristics for each type of bond, intermolecular force, and relative to each other, how strong or weak they are. And I know that it says weak on the dipole here, and it's true. An individual dipole interaction is relatively weak. They're stronger than London dispersion, but it's the sum total of dipole interactions between thousands and millions of molecules that really add up and affect things. Okay, I'm actually going to skip over this graph. We just really don't have time for it, and it's not necessarily one of the main points of chapter 8. It's a figure in your textbook if you do want to read about it. The interesting point here is just we were asking the question, why is the boiling point of water, because this is measuring boiling point, why is it higher than even HF? And I told you I'm going to skip over it. It's not important. It just has to do with the number of acceptors and donors that are on hydrogen versus they're even on a water molecule versus HF. But anyways, moving on. Okay, so that's kind of the end of the intermolecular forces part. Now we're going to talk about gases, and the rest of lecture today is going to be spent on gas laws. So we're going to talk about a lot of different kinds of gas laws and how they work. So talking about gases, first off, we're going to use 3 properties to measure gases and understand gases. Here are the 3 properties. We're going to use temperature, we're going to use volume, we're going to use pressure. What is pressure, by the way? How do we define pressure? If we're thinking about pressure, I got a picture of a tire here. We know tire pressure is important. I'm thankful for my dad. He always, like, anytime I pull up at my parents' house, anybody like your dad or somebody's always like, your tires look low. But I'm thankful, because if I got on the road and I had a flat tire, well, I'll never will, because they always are checking for me. But tire pressure is important. But what creates tire pressure? Allison, that's the unit, pounds per square inch, PSI. We're going to talk about that. What creates pressure on the tire and keeps it inflated? I know you've wondered this so many days of your life. The air molecules, okay, that we put into the tire, there's air in there, and those molecules they're gas, they're flying around, and they are hitting the walls of the tire, and that is creating pressure on the tire. That's what keeps your tire inflated. So pressure is this. How do we define it? It's a force per area. Okay, in your tire, the force is the molecules hitting the walls of your tire, and the area is the essentially the volume of the tire. Okay, I have another picture over here. Does anybody know what a picture of these are? Helium tanks, helium tanks, helium tanks. Well, they could be. Likely they're not helium tanks, but they are in a helium tank. What do you know? You have a lot of helium pressed into that tank. I think I told you guys I bought a helium tank for my daughter's second birthday because I didn't want to pay $60 to blow up balloons. Okay, I just wanted to pay less than that. So you can have helium tanks, but these you can also condense many, many, many other gases. So you can have nitrogen tanks, oxygen. I have no idea what gases are in these tanks, but they are pressurized gas tanks. Okay, these are pressurized. So you see the gauges up top, all these gauges indicating what the level of pressure is in the tank. Now, I will tell you something, being in grad school, we had these all over the lab because there's times where you maybe need nitrogen or you need oxygen for whatever research you're doing. You'll see these in hospitals. Any research lab you walk into, you might see pressurized gas tanks. But does it concern anybody that there are chains here? Anybody notice those? Why are these gas tanks chained to the wall? I mean, they're not going to run off anywhere, right? It's just air, so it's not like they're super valuable. Okay, it's not like taking an instrument or some very expensive glassware. It's just air in those gas. So why are they chained to the wall? Here's why they're chained to the wall. The amount of pressure in there sometimes can be upwards of, say, 2,000 pounds per square inch or more. Okay, your tire pressure is 34. That's a regular, typical 34 psi is a good tire pressure. So 2,000 or higher psi, that's a really, really pressurized. So here's the deal: if something causes to explode, these things could probably bust through concrete walls. So that's why they're chained to the wall. Because if they were around any sort of heat, like if the building caught fire or something, we kind of want to lock those down in place as best as possible. Because pressurized gas can be very dangerous. So that brings up a unique property of gases. We can force gases into small spaces. All right. Why? Because there's so much space already between gas molecules. Remember, like solids, they're not forced together really close. And because there's air and space between those gas molecules, we can force them together. And that's how we get pressurized gas tanks. So that's a unique point of gases. We're actually going to look at how the volume and the pressure change when we do like force gas molecules close together, or when they are allowed to space out more and more. How these three properties change as we adjust one or two of the variables. Okay, so we're going to look at, there are many, I don't know why there are so many units for pressure. I literally ask myself that every time I teach this part of the chapter, and you're going to be asking yourself the same thing. Why are there so many units for pressure? I don't know, but there are, and we need to be aware of some of them, not all of them. So just know that I'm not even showing all of them to you. I'm just showing you some of them. The first one Allison actually mentioned in the chat is PSI. Okay. PSI is abbreviated. It stands for the pounds per square inch. And we're familiar with that because of common things like tire pressure. Okay. Pounds per square inch. All right. That's how tire pressure is measured. So that's one unit for pressure, PSI. Pounds of air being the force on the area of whatever it is that they're pressing against. But if we go down, this next picture on the next slide is going to introduce another unit to us. You see the world, okay, the Earth, and you see this column here. What is that? It's extending out into the atmosphere. And we have gravitational force, we know, on the Earth. So at all times, everything is being pulled down on Earth. So I'm going to read this little paragraph to you. It says, the air in the atmosphere above you puts pressure on you. You thought it was your chemistry class that was stressing you out and making you feel so weighed down. It's not, it's the atmosphere, okay? This actually blows my mind. Everything around you feels this pressure. In fact, 1 square inch of you has 14.7 pounds of pressure. Now, it doesn't feel like anything to us because this is no odd, but isn't that astounding? 1 square inch of us has 14 points. Go pick up a 14.7 pound weight and then tell me if that's how it doesn't, it's normal for us, but that is the truth. So 1 square inch has 14.7 pounds of pressure at sea level. Now, obviously, if you go climb Mount Everest, you're not going to have that much pressure because your elevation, this changes with elevation, okay? But at sea level, it's 14.7. So atmospheric pressure, we call it 14.7 psi. So we have actually just created a conversion factor here. 1 atmosphere, that's another now unit of pressure, okay, is 1 atmosphere, 1 ATM, ATM standing for atmosphere. So technically at sea level, 1 atmosphere is equal to 14.7 psi, okay? So I want you to remember those 2 units and how they relate to each other, but we're not done. This is a more sciencey, this is a more chemistry oriented unit for pressure. And it's derived from this column mercury. So it's it's a very simple machine, actually. I'm not even going to call it a machine, just instrument. You have a dish, a little Petri dish. Anybody use those in like high school biology? You're like, no, we didn't do much in high school. Some people are like, we didn't do a whole lot in high school biology. But if you did, oh, I'm catching up on the chat. How can I lose that? Sometimes I feel it in my stomach. I know that pressure, you don't realize, but it can get to you. So here's a Petri dish and it's just got mercury in it, okay? And you have a column, and because there's atmospheric pressure pushing down on that mercury, it will force some of the mercury up into the column. And big whoop, right? Why does this matter? Well, this is just how we measure another unit of pressure. At sea level, at 1 atm of pressure, they found that the mercury goes up the column 670 millimeters. Y'all recognize that unit, right? millimeters. Okay, so they measured this distance and they found that it was 670 milliliters. So because of that, what we found out is that 760, I was saying that backwards, 760 millimeters of mercury. They also honor the guy who invented it. They call it a torr. I'm not going to make you memorize a torr, but they're equal. 1 millimeter mercury is 1 torr, is equal to 1 atm. Okay, so now we have like 4 different units for pressure. We have units called millimeters of mercury, and that comes from this little Petri dish instrument. They also call those units a torr just because of the guy who invented it. So those are equal, 1 to 1. And 760 millimeters of mercury, mmHg, is equal to 1 atm, is all equal to 14.7 psi. And you thought we were done, but we're not. I told you there's a lot of units for pressure. Finally, though, I will tell you, this is the last one. We have the SI unit because we have to have an international system, an international way to communicate pressure. And we call it the Pascal. Pascals are the smallest. So 1 atm, actually, here's our number down here, is 101,325 pascals. Now, the only reason I'm showing you this is because I know we have talked about SI units and why they're important. Okay, they're important because people do research all over the world, and we're very, very thankful for that. We just have to have a way to communicate our measurements with consistent units, and pascals are that consistent units. If you read research papers and articles, in fact, as you do some research on gas laws, you might come across PA, and I want you to know that that stands for the Pascal. Okay, here's the only ones I want you to know. I just want you to be able to relate these things. 1 atm to 760 millimeters of mercury is this many pascals, is that many psi. Okay, there's sometimes, if you ever see a kPa, that is just a kilopascal, okay? And you guys know what kilo means, okay? 1 kilopascal is 1,000 pascals, So if you see that in a paper as you do some research, don't be confused by it. It's just a kilopascal. But you don't have to memorize kilopascal. So I just want you to know how these relate. And again, you have this slide for any quiz or any exam. You don't have to necessarily memorize all these. We will be pretty frequently converting between these units for these next things we're going to do. Okay, any questions on pressure? So let's actually do a conversion. We're going to work this problem. It says your tire pressure is 34 psi. Good, that's good tire pressure. What is this in millimeters of mercury, pascals, or atmosphere? So the first thing we're going to do 3 conversions here real quick. We're going to convert to millimeters of mercury. So 34 psi. We want to convert to millimeters of mercury, so we need to relate how many psi equals how many millimeters of mercury, and we have the numbers right here. 14.7 psi is 760 millimeters mercury. And because those two are related, we're just going to plug them in as a conversion factor. And which units do we want to cancel? PSI. Thank you, Aaliyah. So we'll put the 14.7 psi on the bottom and the 760 millimeters of mercury on the top. And now you just do the math. The PSI cancel out. So you'll do 34 times 760 divided by 14.7. And you should get a whopping 1757.82. Is that what y'all got? Okay, thank you, Abby. Yeah, thank you, Ken. Okay, good. A lot of y'all are getting that. So just a little one-step conversion problem here. The reason I'm introducing these is because once we actually get to the gas laws, there may be times where you have to do a little conversion on the front end to make sure you have right units before you plug stuff into your gas law. And all you're going to be doing is stuff like this, okay? It is one added step, but it's just usually a very simple one-step conversion. Okay, what is it in pascals? So now you can honestly start either place. You could pick this number or this number and convert to pascals, but we'll just stick with the 34. So now we're going from PSI to pascals. So we need the relationship. We know it's 14.7 PSI. That number didn't change. But how many pascals is that? And the number is right there, 101.325. And that's not a decimal, that's a comma. So it's not 101.325, it's 101,325. So we'll plug those numbers in. That's a big number. Well, 2, 3, 4, 3, 5, 7.14. That's a lot of pascals. And it's a lot of pascals because pascals, remember, are the smallest unit. Okay, lastly, the conversion to atmospheres is the easiest because it's 1 ATM that's related to all these other numbers. So start again, 34 PSI. How many atmospheres is this? Same number on bottom, 14.7 PSI is this time just 1 ATM. And where am I getting these numbers? I'm just looking right up here. Everything that's related, okay, is right there for you. PSI cancels. So it'll be right under 2 ATM, 2 or over, okay, 2.3. Okay, easy enough, not too bad. I know it's a lot of units, but usually you're just making sure you got things in the units you need to plug into the gas laws. So that leads us directly to the gas laws. We have arrived. All right, what the gas laws are, kind of an intro to gas laws. Or I guess before I move on, any questions on those conversions? Any questions on why we picked the numbers we did and how we did that? Okay. Combined gas law. So from the name itself, this tells you this is a combination of multiple gas laws into one ultimate law. Okay. So the combined gas law is actually 3 other gas laws all put into one. And we'll look at those 3 individually. But the gas law kind of, it's the most, not cohesive. What's the word I'm looking for? Comprehensive. That's the word. It's the most comprehensive. So it's the one that kind of is the most useful. What you can see it is, you got 2 sides here and you got lots of different letters. Okay. What do these letters mean? Well, remember that we study gases with 3 properties: volume, pressure, and temperature. So we've just abbreviated those 3, and we're seeing now how they're all actually interrelated together. So on one side, we have P1, V1 equals T1. And these would be what we call the 1 stands for initial conditions. Okay, so this means we have some gas at some initial set of conditions, a certain volume, a certain pressure, a certain temperature. And what they found is that if you change one of those variables and you have a different set of conditions, there's ways that they're equal. And so that's what the 2 means. The 2 just means the final conditions. Okay. And then P stands for pressure. V stands for volume. And then T is the temperature on both sides. Okay. So when we're talking about the gas laws and how all these things are related, they help determine changes in a gas's physical properties. Okay, the physical properties being the actual volume and the actual pressure and the actual temperature. Okay, so we can, if we change one thing, we can use this equation to see how the other things were changed. All right, and then obviously it's describing the relationships between these 3 units: pressure, volume, temperature. Okay. So what we're going to do next, though, is to see how we came up with the gas law. We're going to look at the 3 individual gas laws that we combined to get this law. And so the name makes sense because what we did is we took, and y'all maybe have heard of these names: Boyle's law, and then the other one. Does anybody know the other 2? If you're looking at your lecture notes, you'll see them.
Is it Gay?
Gay-Lussac's is one. And then Charles' law. Yep. Thank you, Caitlin. Charles' law. Charles, Gay-Lussac's, and Boyle. So Boyle's law. What is Boyle's law? Well, it is a relationship only considering pressure and volume. We're leaving temperature out of it. Okay. This is an A and B conversation. You can see your way out. Anybody said that to somebody before? Yeah. You're like, yeah, when I was in middle school. I'm past that. Okay. Combined gas law. We're just looking at pressure and volume. That's Boyle's law. So what is what we're asking here, essentially what we're doing is, what does the combined gas law look like when the temperature is held constant? So the reason we can, in 5th grade, Ella, the reason we can leave temperature out of this is because temperature is just not changing. It's going to be held constant. So we're just going to look directly at how pressure and volume are related. So here is Boyle's law. I love pictures. I'm a visual person. So these are right from your textbook, and they really do help me understand it. If you have a container with a movable lid, okay, like a plunger, like you could push down on it or you could lift up on it. That's what we're pretending this container is. And the green stuff inside is our gas. So if we have an initial set of conditions, say we have 1 liter of a gas, it doesn't matter what gas it is, but 1 liter of a gas, and it is held at a pressure of 1 atm. Okay, it's exactly what we feel right now, this kind of pressure. Okay, doesn't feel like a lot of pressure, but it's 1 atm. What would happen if we increase the pressure? Well, how do we do that? We could push down on the lid. That's going to increase the pressure inside the gas or inside the container. What if we do that until we have 2 atm of pressure? So essentially we've doubled the pressure, right? 1 atm to 2 atm. What's going to happen to the volume? Well, to increase the pressure, we had to decrease the volume. If we're not changing temperature, to increase the pressure, to double the pressure, essentially, look what happened to volume. Volume got cut in half. So the relationship between pressure and volume is this simple. If you increase one, you have to decrease the other. Okay, vice versa. If we start on this side, the right side, with a small volume, and we increase the volume, what did we do to pressure? If we're going this way, if we increase volume, we decrease pressure. Okay, so if you increase one, you decrease the other. If you increase the opposite, you'll decrease the thing, the opposite property. So pressure and volume are inversely related or proportional. And this little squiggle mark, that's what it means. It's just telling you how they're related. Pressure is proportional. This symbol means proportional to 1 over the volume. Okay, if they were directly proportional, then as you increase one, you would increase the other. And then we would say P is proportional to V, but that's not the case. When you increase one, you decrease the other. So P is proportional to 1 over volume. Okay. Now, PV equals a constant. What does that mean? What is that saying? Well, essentially, what is Boyle's law? I actually don't have it on here. Boyle's law, we're just going to write it right up here. If we're taking temperature out of the equation, we're just going to literally delete T. What do we have left when we do that? P1 V1 equals P2 V2. That is Boyle's law. And if we want to prove that to ourselves, let's just literally plug in the numbers we have from our figure below. Here's our P1, that's our initial pressure. Here's our V1, that's our initial volume. And then over here is our P2 and our V2. So let's just literally plug those in. 1 times 1 equals 2 times 0.5, right? Did you get 1 on both sides? So mathematically it holds. So these equations are actually, the math is very simple. You just have to make sure your units match. If you have 3 of the 4 pieces, if I give you an initial pressure and volume, and then I say, at a new pressure, what's your new volume? You could solve for that, right? We're actually going to do that on the next slide. Any questions so far on Boyle's law? Good? Okay. So speaking of, how did this relate to any health sciences? This is an article, if you want to go read more on it, that I was reading up on. It's brand new this year, so that was cool. It's pretty current. So this is actually going to use some health sciencey words, some nursing words that I am even less familiar with, but I wanted to show you how these two relate, because I think that's important. You know, a lot of you guys, you're taking a very hard chemistry class and you're like, how is this even really going to benefit me? I'm just taking it to check off a box, okay? But I want you to know it really does relate. So using Boyle's law, P1 V1 equals P2 V2, we can calculate the change in volume at different altitudes, because as you go up in altitude, what happens to pressure? Like the pressure on you, that gravitational force, the atmospheric pressure decreases as you go up in altitude. Now, how does this relate to stuff like health sciences? Okay, so think about this. Sometimes people can have a lung collapse. Anybody know somebody that maybe has had a lung collapse before? And why does that happen? It happens for different reasons. But one reason it can happen is in your chest, between your lung cavities, or in that space, that cavity space, you can have air get trapped. Somehow, some crazy things can happen, and you could have air in places that you're not supposed to have air. And I forget what I think they call that, from my understanding, a pneumothorax. Did I say that right? Anybody? No?
Pneumothorax.
What is it?
You said it right.
Okay, pneumothorax. Thank you. Y'all are teaching me now. You call it a pneumothorax. So if you had to med flight this someone, say they were in an accident or whatever, and they needed to get to hospital quickly, a lot of times they use helicopters, right? And so if you are going to fly this somebody, you're going to be changing their altitude. Okay, so you have air inside their body at a certain pressure, and then we have air outside the body at a different pressure. Okay. And so it's very important if the volume and pressure are related, and as you increase one, you decrease the other. If we are decreasing atmospheric pressure because we're changing their elevation in a helicopter, we're getting them off the ground, how's that going to affect the amount or the volume of that air inside their lung cavity? Because if that expands too much, that could collapse a lung. Okay. So that's kind of what this problem is getting at, and showing you how it applies here. So I'm just going to read this. We can calculate the change in volume at different altitudes, meaning of the pneumothorax. For example, a patient with a simple pneumothorax being airlifted to their local hospital. They have a pneumothorax with a volume of 1,500 milliliters. And remember, milliliters is not big, it's about the tip of your pinky, but 1,500 of those, that might add up a little bit, at sea level. Okay, so there it is. And I told you we'd run into this unit. What is a kPa? That's a kilopascal. Okay, that's why I just wanted to at least show you what it was. Okay, and so if we're at sea level, we also know that's 1 atm. Okay, remember that. So that's the initial, that is our initial parameters. We can go ahead and define that. V1 is 1,500 milliliters. That's our initial volume. P1 is the 101.3 kPa at an altitude of 1 kilometer. So they get them in the helicopter and they're 1 kilometer above the ground. Here is our new pressure, 90 kPa. So that's P2. Anytime you get some new information, it's a new variable. So this is 90 kPa. Now, assuming the patient remains at a constant temperature, we're going to calculate the new volume of the pneumothorax. How much does it expand, or does it shrink? And what would it do? If we are, what's happening to volume? We are decreasing, or sorry, what's happening to pressure? We are decreasing pressure. And what do we know? If we decrease pressure, what happens to volume? Volume is going to increase, and we don't want it to increase a lot. So let's see how much it will increase by. So you're just going to simply take, here's our equation, P1 V1 equals P2 P2. Plug everything in. And what's essential here, what's critical here, is that the units of pressure are the same. If your P2 was units of ATM or PSI, you would need to convert it one way or the other so that your units of pressure are the same. P1 and V1, or sorry, P1, P2 have to have the same units, as well as if we were plugging in two different things of volume, they just need to have the same units. But here we don't have to do any conversions, they're already the same. So you should have 101.3 kPa times 1,500 milliliters. So that is our P1. P1 equals P2, which is 90 kPa. That was P2. And we're looking for V2. So I'm just going to write V2. You could write X or whatever. Anybody have our answer? First off, how do we solve for this? We just divide both sides by the 90 kPa. And that's how we solve for V2. And then what do you notice? Units of kPa cancel out on this side, and this whole term goes away because you have it on top and bottom. So y'all got 1688.33 milliliters. So V2 is 1688.33 milliliters. Okay, so that pneumothorax increased in size. Now, probably what's more useful if you're on a helicopter is to say by what percentage did it increase? Is this a 50% increase, a 10% increase? Because there's probably different levels. I'm pretty sure they said it like a 30% increase that can become more fatal, and you could end up with a collapsed lung or something. So how would we figure out by what percent did it increase? How could we figure that out? Well, you do the 1688.33 divided by 1,500 times 100, you should get a percentage. Is that right? Sorry, flip this. There we go. That should give you the percentage of increase. That doesn't sound right. 88% increase. We're missing a step.
Would it be the complement of that?
15 or 12%. You know what? I bet you're right. What we could do is subtract, find the actual difference in those numbers. 0.33 minus 1500. So it increased by 188.33 milliliters. And then if we wanted to see 188.33 is what percent of the original 1500 times 100. I bet you'll get the inverse of that. So 188.33 divided by 1500 times 100, you should get, it was a 12, that makes more sense, 55% increase. So let's say they're like a 30% increase is fatal or whatever. You could say, well, we're still in a safe zone here, but we don't need to fly much higher, okay? Any questions on that? I found this actually be very interesting. So that was just with Boyle's law, by the way. There's many other opportunities and examples here. And so we're going to look at the next one, Charles' law. Any questions though before we move on? Am I moving too fast? We doing okay? Okay, Charles' law is relating what? Temperature and volume. So guess what we're holding constant this time? Pretty much with all these three laws, we're holding one variable constant. We're seeing how the other two relate. So here, we're holding pressure constant. Okay, what is the combined? We're asking the question, what does it look like when the pressure is held constant? So if we take pressure out of the equation, what we have left is V1 over T1 equals V2 over T2. That is Charles' law. And again, with our picture of our movable lid container here, if we're just examining volume and temperature, let's say our initial conditions, our V1 and our T1 are shown. So say we have 200 Kelvin as our temperature, and our volume is half a liter, 0.5 liters. And our pressure here is going to stay constant, 1 atm in both cases. If we heat it up, so we're increasing temperature, what's going to happen to the volume? Well, if we're trying to keep this at 1 atm pressure, as we heat it up, the volume is going to increase. Think about what you're doing to gas particles. If there's a whole bunch of little tiny particles in here, the gas particles, they're so small we can't see them, I know. But if we could see them, when you heat something up, you're making them move even faster. And if they're moving faster, they're going to collide with the walls of your container more often. And collisions, that's what creates the pressure. So if we're increasing the heat to keep pressure constant, we have to give them a bigger space to move around in. That way, their frequency of collisions stays the same and the pressure stays the same. Okay, if there's more space to move around in, chances are they're not going to collide with the walls more often. So if essentially what's happening though, as you increase temperature, you are increasing volume. So temperature, if it doubled to 400 K, volume would double from 0.5 liter over here to 1 liter on the other side. So as you increase temperature at constant pressure, you increase volume. So temperature and volume are proportional. Directly proportional, not inversely proportional. And that is why you see the T squiggle V, not 1 over V. And if you're curious, this is actually how hot air balloons work. I'm looking at our time here and trying to be mindful of that. So I'm not going to get into that exactly, but this is explained really well in your book. And I just think it's a great example of understanding Charles' law. So I encourage you to go read about it in the section corresponding to Charles' law. Any questions on Charles' law? Okay. Gay-Lussac's law is the third and final of the individual gas laws that are combined in our combined gas law. Here, we are holding the last variable constant, which is volume. So what happens when the volume is held constant? Because we're just examining with Gay-Lussac's law changes with pressure and temperature. Changes with pressure and temperature. So we are going to hold our container this time at the same volume. We're not going to allow the lid to move. We're going to keep the volume constant. So if we are, what is Gay-Lussac's law exactly though? If we're taking volume out of the equation, we're holding it constant. So we'll just delete volume from the combined gas law and we get P1 over T1 equals P2 over T2. So the lid on our container stays fixed volume this time. So 1 liter in both cases. And if we have a pressure of 1 atm and a temperature of 200 Kelvin, that's our P1 and our T1. If we double the temperature, if we heat it up, guess what happens to pressure? This is a typo here. It should be 2 atm. If we double temperature and we heat those gas molecules up and now they're moving around even faster, but they have the same amount of space to move in, the pressure will double because they're colliding with the walls of that container. Should be proportionally double the frequency. So double the pressure because it is collisions again with the container that create pressure. So temperature and pressure are proportional as well. Okay. So that is all the individual gas laws, and together is where we get P1 V1 over T1 equals P2 V2 over T2. Okay, any questions with those 3 gas laws?
So the last one, the Gay-Lussac's law, temperature and pressure are directly proportional?
Directly proportional. If you increase one, you increase the other. And then same, Gay-Lussac's and Charles' law are similar that way. If you increase one variable, you increase the other. It's Boyle's law that is the one that's inversely related. If you increase pressure, you decrease volume, and vice versa. If you increase volume, you decrease pressure. The other 2
I have
are.
a question.
Yeah, what's up, Allison?
Like, does the temperature always have to be like in Kelvin, Celsius? Like, what's the
Yeah.
deal with?
Great. We were going to get to that when we actually work a problem with the whole combined gas. You're good. I'm glad you asked that though. Temperature always needs to be in Kelvin. Okay. Do not do these in Celsius, and especially don't do it with Celsius on one side and Kelvin on the other. Okay. I'm going to make a note. Temp in Kelvin always. Okay. The way you will miss points on an exam for problems like these are if you mix up the units. Okay. The math is really not hard. It's just some algebra. But the units will get you if you forget to convert and keep your units the same on both sides. Pressure and volume we're not as picky. Like you could have units of liters for volume on both sides, or you could do units of milliliters for volume on both sides, as long as they're the same on both sides. Does that make sense? With pressure, you have so many different units to pick from. Now, if I give you 2 different units of pressure in the problem, like I give you ATM for P1 and millimeters of mercury for P2, that's when you'll need to do what we did up here. And you'll just need to do a simple conversion first, get them both in the same units, and then you can plug everything into your problem. Okay. All right. Guess what, guys? Are you tired of gas laws yet? Well, we have more. There's a lot of gas laws. So volume and molar amount, which is Avogadro's law. And here's the deal, for that bonus point thing, you can, if you find something on a particular unique law, like it doesn't just have to be here's how the combined gas law applies. That problem we worked earlier was here's how Boyle's law applies. So if you find one for Avogadro's law, any of these gas laws, how does it relate to health sciences, period? I'm more than happy to give you points for the effort you put into finding that out. Okay, but what is Avogadro's law? It is a relationship between volume and molar amount. Okay, now this is a very silly, dumb example, but I think it illustrates the point just fine. Essentially, what Avogadro's law says, that the more gas you have, the more volume it would inherently take up, right? So which balloon has more helium in it? If these are helium balloons, the blue or the red? Red. And which balloon is bigger? Red. Okay, the more gas you have, the more volume it should take up. Now, we actually haven't quite addressed the question. Volume and molar amount. When I'm saying the amount of gas, we're talking about the number of moles of gas, okay? So the more, I guess instead of saying the more gas you have, I should say the more number of moles of gas you have, which directly relates to the volume of the gas, okay? The more moles of gas you have, the more volume that gas will take up. Right, so Avogadro's law is at constant temperature and pressure, the volume of a gas is directly proportional to its molar amount. So that's literally what we just said when you say the more volume you have, the more moles of gas that are present, or vice versa. The fewer moles of gas you have, the smaller volume they'll take up. That's what we're saying. We're just holding temperature and pressure, two variables, constant here. So to abbreviate these properties or these variables, V is the abbreviation for volume, N is the abbreviation for number of moles of gas. All right, so Avogadro's law, what we have, sorry, I'm moving one thing around, is V1 over N1 equals V2 over N2. Okay. And as you increase the number of moles of gas, the volume of the gas will increase. All right. Now, with Avogadro's law, one little caveat that we haven't run into before I wanted to explain is that I'm going to read this. To simplify comparisons of gas samples, different gas samples, it is convenient to have a set of conditions known as STP. What is STP? It is a standard temperature and pressure. If we're holding temperature and pressure constant, it makes things a lot easier if we just pick the same temperature and pressure, standard temperature and pressure. And that way we can compare these relationships between different gases a lot easier. So if we are doing these kinds of gas laws or experiments at standard temperature and pressure, here's what that means. We have 0 degrees Celsius or 273.15 Kelvin and 1 atm. That is standard temperature. And that is standard pressure. Okay. Now, they have already defined for any gas, it doesn't matter what gas it is. It could be oxygen gas, helium gas, nitrogen gas, doesn't matter. But at standard temperature and pressure, 1 mole of any gas has a volume of 22.4 liters. That's quite a bit of gas, right? 22.4 liters. That's a standard molar volume. For 1 mole of any gas, the volume of that gas is 22.4 liters. So just remember these conditions. Why? Because I'm going to give you a list of textbook problems. As for extra practice, these are not an assignment. This is not mandatory. This is if you want to practice some problems this weekend to prepare for exam 3. There will probably be problems in your textbook that say at STP, what is the blah, 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 okay? And I want you to know what STP is. So you just plug in, you would plug in that temperature and that pressure in your problem to solve it if it says at STP. All right, this is essentially, look at all this information. We've covered a lot, okay? This is essentially the culmination of the gas laws minus one more. Hang with me. I know we've got one more though, and then we really are done. The one I think, again, is most useful is the combined gas law. And I used to tell people memorize it, but all of your exams this semester are open note. So just as long as you know which one is the combined gas law, you really honestly don't have to memorize much of anything this semester. But there's kind of a summary, all the gas laws on one page. The last one I want to talk about in our remaining, what do we got, 7 minutes, is the ideal gas law. And then really you know what, we're probably going to have to skip over partial pressures since we're not going to get to it. I'm trying to see how many slides we have left. here's what I'm gonna tell you. Anything we don't get to today is just not gonna be on the exam, okay? I'm not gonna make another video and say, learn this too. To be fair, anything we don't get to, I'm just not gonna put it on the exam, okay? So we will finish with the ideal gas law, and we will have ideal gas law problems on the exam. And it really is just kind of a plug and chug type of thing. So the last thing I want to tell you about ideal gas law, this is a relationship between all the pieces together. So we've been looking at pressure, volume, temperatures. We also did Avogadro's law, where we have molar amount, and we haven't worked practice problems with these just yet. But in the help sessions Friday and Monday, guess what we're going to be doing? Working practice problems with gas laws, so you get comfortable with them. But I at least have to tell you this law. So P, it's a relationship between P, V, and T, pressure, volume, temperature, and N, number of moles of gas. So the ideal gas law is just combining everything. Okay, so it's even a little more comprehensive than the combined gas law. And here's the equation. PV equals nRT. PV equals nRT. That is the ideal gas law. You also might see it written in your book another way. It might say R equals PV over NT, but this is the same thing. We've just moved N and T to the other side of the equation. This is the same thing. So if you see this one in your book, just know it's the same as PV equals nRT. They just move the variables around. Now, what is R? Because I told you that the relationship here is between PV, T, and N. R is a constant, okay? So for this relationship to work, we have this constant. It's called the gas law constant. Is a constant whose value in units don't change. And this R, this constant, has a set of units, okay? For different kinds of units and pressure, you'll see different values of R. So if you were to Google R, the gas law constant, there are kinds of R's with different units, and it'll be a different number. But the one I want you to use for our problems and on our exams is this R, 0.0821. And here are the units. This is the most units I think we've ever had on one variable. This is 4 different units. We've got units of volume in liters. So that's our units for volume. We've got units of pressure in ATM. Number of moles is just the unit there is moles. And the unit for the temperature variable is Kelvin. And this is where this gas law becomes complicated. Because what that means is for you to plug anything into this equation, you have to have the exact same units as R. So if you're going to plug in a volume, guess what units your volume have to have? It has to have units of liters. If you're going to plug in a pressure, you've got to plug it in with units of ATM. If you plug it in with units of PSI, you're not going to get the right answer. So anytime you use the ideal gas law, you have to use the units that match on R, okay? So in our last 3 or 4 minutes, we're going to just do this one practice problem to show us and get us comfortable with how do we use the ideal gas law? What kind of problem would I put on the exam when you're going to have to use this? And here's a perfect example problem. It says, how many moles of air are in the lungs of an average person with a total lung capacity of 3.8 liters? Assume that the person is at 1 atm pressure and has a normal body temperature of 37 degrees Celsius. Okay, how many moles of air are in the lungs of someone with this volume, this pressure, and this temperature? So the thing you have to do is say, what variable am I trying to solve for? Am I trying to solve for P? Am I trying to solve for V? Am I trying to solve for N? I'm never trying to solve for R because R is a constant. You just plug that one in. Or am I trying to solve for T? Well, if you're given a variable, then you're not trying to solve for it. And I'm seeing in the chat, yes, we are trying to solve for N. It says how many moles? And remember, moles are represented with N. This is a volume. N is the number of moles. Okay. So to solve for N, just like we used to do with the specific heat problem, we're going to get N by itself. We want N on one side of the equal sign by itself. So if I take PV equals nRT, I'm going to rearrange my equation and I'm going to solve for N. So to do that, I'm going to divide both sides by RT. Now R cancels out and T cancels out. And I have PV over RT equals N. Okay. Now, can we just plug everything in? We need to make sure the units on the numbers we're given in the problem. So where's our volume? Here's our volume. Here's V. Where's our pressure? Here was our pressure. Here's P. I like to go in, by the way, and do this. I like to label my problem. It helps me. And then here's our T. And what I notice about T is we have units of Celsius. What units do we need to have? Look at our gas law constant. We need to have Kelvin. So the one extra step you got to do for this problem is you've got to convert your temperature to Kelvin, and then you can plug everything in. So I'm going to take 37 degrees Celsius. I'm going to add 273.15, and I'm going to get my temperature in Kelvin. And I think that is just going to be 300.15. Is that what y'all got? 37 plus 273.15 should be 300.15. Now I have the proper units on everything. I've got liters, ATMs, and Kelvin. So now I can just plug it all in. So let's plug in pressure. That goes first. 1.0 ATM of pressure.
I got 310.15 on the temperature.
Oh, you're right. If it was 27, it would be. Thank you, Leah. Thank you. Okay, so plug in pressure up top times the volume. It's P times V on the top. So we're going to plug in 3.8 liters. We're going to divide that by R and T. Divide that by R and T. So we're going to plug in R, the whole thing. And all the units. This gets messy. So leave yourself some space when you work these. Liters times ATM over mole times Kelvin. And that is R, and R is multiplied by T over here on the bottom. So we're going to times our temperature in Kelvin, 310.15 Kelvin. And I know we're at time. We're just going to get the answer, and then we're done for today. So 1 times 3.8, and then here's the deal too. Put this in parentheses in your calculator. If not, you will not get the right answer. You'll divide by R, but your calculator will actually multiply by T unless you put it all in parentheses. If you're doing it all at once. Sometimes people like to multiply R and T, get a number, multiply P and V, get a number, and then divide the two. That's fine. But 1 times 3.8 divided by 0.0821 times your temperature. Anybody have the answer for us? That equals N. 0.15, so that equals 0.15 moles, okay? And to double check yourself, do all your units cancel properly? ATM on top, ATM on bottom, liters on top, liters on bottom, Kelvin here, Kelvin on bottom and the bottom, and we're left with 1 over moles, which is just moles. Okay, we're a minute over, so that was a lot. If you need to rewatch any of this, make sure you